In this video, I want to talk about the effect that temperature has on a chemical equilibrium. And I'm going to show you a very useful trick that can be used to help solve temperature equilibrium problems. Because out of the four factors that affect a chemical equilibrium, temperature is by far the most challenging to grasp. Now you'll usually be given a question such as this. You'll be given a chemical equilibrium and a delta H value, and you'll be asked to determine what effect increasing or decreasing the temperature has on the reaction. So in order to show you this trick, I quickly want to review an exothermic and an endothermic reaction. So we know that an exothermic reaction feels warm. And we also know that delta H values are less than 0 because the system loses heat. And because the system loses heat, energy can be considered a product. So we can rewrite an exothermic equilibrium like this. The reactants are in equilibrium with the products and energy. And for an endothermic reaction, we know that they feel cool, and we also know that delta H values are greater than 0. And because they're greater than 0, energy can be considered a reactant. So any endothermic equilibrium can be rewritten like this. Reactants plus energy are in equilibrium with products. Now I'm going to show you the trick. You'll notice that I wrote these equilibrium arrows in opposite directions. The top ones are in opposite directions and the bottom ones are in opposite directions. And I did this on purpose. So I always, when solving temperature equilibrium problems, I always write the bottom arrow pointing in the direction of the energy variable. The next thing that I do is I color the bottom arrows blue. Bottom blue. And I color the top arrows in a reddish color. And the blue, to me, it just represents cold, and the red represents hot. Okay? So, if we have an exothermic reaction, and we're cooling it down, this is what I do. If we have an exothermic reaction and we cool it down, I think of it as removing energy. So we remove energy, so I draw a blue arrow out of the page because we're cooling it down. Okay? But if we have an exothermic reaction and we're warming it, I think of that as adding more energy to the reaction. So I draw an arrow in like that. Okay? So whatever process is being done, if we're warming it, this arrow will point in, the red arrow will point in the direction that the equilibrium will shift. But if we're cooling it, the blue arrow will point in the direction that the equilibrium will shift. Okay? We can do the same for an endothermic reaction. So if we're warming an endothermic reaction, I think of it as adding energy into the page or into the reaction. So whichever direction this red arrow is pointing is the direction that the reaction will shift. The direction that the equilibrium will shift if you warm an endothermic reaction. But if you cool an endothermic reaction, The blue arrow will point in the direction that the equilibrium will shift upon cooling it. So let's go back to the original problem that I showed. So we're given this equilibrium reaction. We have a delta H value of negative 21 kilojoules. So it's an exothermic reaction, and we're told that the temperature is increased. So we're warming this reaction. So this can be, so if we want to use this trick, we have to include the energy as a term in the equation. So we can rewrite this equation like this. Carbon dioxide plus hydrogen reacts with the methanol. Sorry, it will be in equilibrium with the methanol and 21 kilojoules of energy because it's exothermic. In an exothermic reaction, energy is a product. So in order to use this trick, remember the bottom arrow has to point in the direction of the energy. Okay? Therefore, the top arrow will point in the opposite direction. I color the bottom arrow blue, and I color the top arrow red. And we're told that the temperature is being increased. So I think of it as adding more warmth. Okay? So that means that whatever direction this corresponding red arrow is pointing is the direction that the equilibrium will shift if the reaction is warmed. So therefore, we can say the reaction will shift left. And that's how you use the trick. I hope you found it useful. If you have any other suggestions for topics you'd like to see me cover, please suggest them.